Going on now to Chapter 3, Section 1, we're dealing with systems of linear equations. And this leads from Chapter 2, where we did standard form of the linear equation in two variables. And now we're moving into what is called system or systems of equations, where instead of just having one equation, we have, let's say, two equations. And here, this equation are the sub 1s, and these are the sub 2. Now, I'll give you a little overview of what we're going to be doing as we look at these various equations. If I were to graph, let's say, this first slide, and then I graphed the second line, we note that these graphs intersect at this point right there. And if I wanted to say this is like 1, and this will be 1, 2, 3, 4, 5, this point of intersection is a -1 and a 5. And what can we say about this? Well, this ordered pair would be a solution for the first equation and would also be a solution for the second equation. So we'd say that where these lines are independent, they intersect at this particular point, and we say they are consistent. So there's some of the vocabulary words that we're going to be using as we go along. Now, if we had another graph, and I'll just do it right here, and I graph, let's say, this first equation, and it looked like this, and the second equation, and it looked like that, we'd say, wait a minute, these lines are parallel, and will they ever form a common point of intersection? And the answer is no. So if you're doing a graph and there are no points of intersection, we say there is no solution. So these graphs are independent, there's no intersection, and we say they are inconsistent. And a third scenario would be in which we had a graph, and if we graph the first line, it looked like that. And then if we graph the second line, even though it didn't look the same originally, and lo and behold, it was right on top of the other, we'd say, wow, it's the same line, just looks a little differently when you see an example later. And there's an infinite number of ordered pairs, that whatever is the ordered pair for one solution is the same solution for the other line. So we say there is an infinite number of solutions, and we usually write it in set builder notation, which will look like this. Put a bracket. We didn't do too well on that, but x comma y, that's your ordered pair, is such that, and then you write out one of the equations. And this equation is actually the same equation for the other, and it's the same line, infinite number of solutions. This is the set builder notation that we use to write it. So there's a sort of a summary of where we're going, and I believe it's 1 through 6 are your vocabulary words, and we'll pick up on number 7. Now for number 7, they're asking us, here's a system of equations. Is this ordered pair a solution for both of them? That is, are they going to intersect at this particular point? And then to check this, what we do is we substitute this into the equation, see if that's true, see if that's true. If it is, the answer is yes. If it's not, the answer is no. So there's our y. 3 times 1 minus 5 equals 2. And then here it's 2 minus 4 times 1 equals a negative 2. So here this is going to be 3 minus 5 equals 2, and we have a negative 2 equals 2. Well, that's not true. And then here we have 2 minus 4 equals a negative 2. Negative 2 equals negative 2. Now, one of them is true, one of them is not true, so this is not a common point. So the answer is no. That is not a solution for this system of equations. For number 8, again, the same thing. Notice this ordered pair is written as A comma B, which we sometimes use. So A would be 3, minus 2, and B is a negative 1, equals 5. And this is 3A, so 3 times 3 minus 10 equals a negative 1. So this becomes 3, negative 2 times negative 1 is plus 2, 5 equals 5, that checks. And this is 9 minus 10 equals negative 1. Negative 1 equals negative 1. This checks, so this is a point of intersection for these two lines. Okay, for 9 and 10, they're asking us to graph these systems of equations to see if we can find the point of intersection. So again, what strategy might you use to put this graph? Well, it's in standard form, so let's use the x and y t-chart. So if x is 0, y is going to be a negative 1. If y is 0, x is 1. And this other one, we can solve for y by simply dividing by 2. And that'll give us y equals 1/2 x plus 1. So in this first example, we're going to use both methods of graphing. So here we have graphing, as you can imagine, is rather delicate depending on the nature of your graph. Here I'm just sketching it. So when I sketched this first one, using my x and y intercepts, I got a dot there and a dot there. And then graphing this equation, y equals 1/2 x plus 1, there's my 1 over 1 up 1, I'm sorry, over 2 up 1, and it intersects right about there, which happens to be 4 comma 3. I'm going to do this other one too because, again, the graph is rather critical. This next one, again, they're using the letters S and T for X and Y. It's always alphabetical. The lower letter in the alphabet would be the X. The higher letter would be the Y. So this is Y equals 3X. Here we're using the X and Y intercept t-chart. And these points are rather close together. So as I was trying to graph it, and I didn't bring my ruler today, and then I plotted this other point, they intersect about here. Now these lines almost look like they're the same, but they're not. I didn't get a good separation. A sharp pencil, and they actually intersect at that point. But this leads us to one of the other things, is that graphing isn't always the best way because it's difficult to graph accurately. Unless you have a nice sharp pencil, a nice ruler, and and you're got to be very careful that you don't go this way or that way too much. But this is the skill they want you to develop. And of course, when you do Math Lab, you have those nice graphs that you can use in the computer. As we do number 11, this is my original equation here. These were our initial system of linear equations. And what I did to this one is I solved for y, putting it in slope-intercept. And then this equation, it's a little bit in slope-intercept. I reversed these. I had to divide by 6. I got this, and then this is my final equation in slope-intercept form. Now as we look at these two equations, if we were going to graph them, notice that here my y-intercept is 2/3, which is about there, and my slope is 2/3. So I would go over 3 up 2. And for the second equation, my y-intercept is 5/6. Well, 5/6 is right there also, just above that, and it's also over 2 up 3. And you might say, well, wait a minute. Here the slopes are the same, but my y-intercepts are different. And from a previous lesson, we said whenever that is true, the lines are going to be parallel. So what would be your solution set for this? Well, we had said earlier that if the lines are parallel, there is no solution. And by solving these for y, we saw that the lines were parallel because the slopes were the same, the y-intercepts were different. And without graph paper, this is particularly difficult. But here we see the original equation. I'm solving it for y, transposing this to the other side, and there it is in slope-intercept form. This was in slope-intercept form, but backwards. I just rewrote it. So my y-intercept on the first one is 6. I went over 1 up 3. And then on this one, I went to 4. Went over 1, then up 2. And when I drew the graph, and again, you need a ruler for this, they intersect at -2, 0. Again, they're using a lot of your graphing technique, and you have to be careful, and you need graph paper to solve this by graphing. Okay, in doing number 13, there's our first equation in slope-intercept form. There's our second equation. It's not quite in standard form, but you could rewrite it. And what I use for this is the x and y intercept t-chart, and I'm just going to plot this from that. So I plot my y-intercept, which is 1. I put a dot right there. Now my slope is 2 over 1, so I went over 1 up 2. So this is sort of the start of my graph. And again, with the ruler, much better. Now when I plotted this, I have 0, 1, which is the same point right there. And my x-intercept is negative 1/2, 0, which is right about there. You might say, oh, wait a minute. That's going through the same line. Should. And this one happens to be the same equation in 2 different forms. So in writing the answer to this is the graph. We see it's the same line. You would write it in set builder notation. X comma y is such that y equals 2x plus 1. And that's going to close out this particular lesson.